We'll now discuss some sorting algorithms that run in linear time, but these only work for very specific cases. In particular, we're going to take a look at bucket sort and radix sort. We've already discussed that any general purpose sorting algorithm in the worst case is going to require omega of n log n time. So if we try to do any improvements, the absolute best, fastest general purpose sorting algorithm cannot be any better than n log n. And that's okay. I mean, that's still pretty efficient, but it would be nice if we could get a linear time sorting algorithm. And the good news is there are some special cases where we can get a linear time sorting algorithm. One such algorithm is what we call bucket sort. Now, in order for this algorithm to work, we need some additional information. So our input is going to be A1, A2, all the way to AN. So we still have a list of items to sort, but these elements must consist of only positive integers, and they all must be smaller than some constant value, which we denote as m. If we can get this extra information, so if we do have positive integers that are smaller than m, the algorithm itself is pretty simple. So we'll have an array which we call count, and this is going to be of size m, and we initialize all the elements to 0. So we say that this array has m cells, or buckets. So we say that these buckets are initially empty. The idea is as we read an element in our original array, so as we read AI, we're going to increment count AI by 1. And so after we do all of this reading, we just simply scan the count array. And what we'll do is we print out a representation of the sorted list. The idea with this is each element gives us the number of that particular element in our array. So like, for example, if A0 is 3, then, or I should say count 0 is 3, that means there are 3 zeros in our original array. So that's all we're doing here. And this algorithm takes O of m plus n time. So m is the size of the array, and n is the number of elements in our original array. And notice that if m is O of n, then that means the total time here is O of n. What we find is this algorithm uses a more powerful operation than just simple comparisons. In fact, the algorithm is essentially performing an m-way comparison in unit time. We can't do this for general purpose sorting algorithms because we can't assume the types of elements that we're going to see. Here we assumed that these are positive integers that are less than m. We can't make that assumption in general. So the decisions that we make are based on the ordering information only. So we can only take a look at what we have as they appear, and we can't take a look at everything at once. In fact, what we find is there are actually several different cases where our input is just small integers. And if we have that, we can take advantage of this bucket sort algorithm, and quicksort is really just overkill, where we really don't need to use quicksort in those particular cases. Another sorting algorithm is called radix sort. Now, sometimes this is known as card sort, and this is because before we had modern computers, this algorithm was used to sort the old style punch cards from back in the 60s and 70s. So here's the idea. Let's say we had 10 numbers that we wanted to sort, and these numbers were in the range from 0 to 99. It really wasn't practical to use bucket sort in this case because we would have 100 buckets, but we only need to sort 10 items. So what we would do instead is we would actually use several passes of bucket sort. So we would first perform bucket sort on the least significant digit. So like if we're dealing with decimal numbers, that would be the ones place. We would then perform bucket sort on the next least significant digit. So that would be the tens place. And then we would do bucket sort on the next least significant digit, and so forth. And what we would do is we would have a list for each bucket. So instead of just counting the number of items that have that same number, we would have a list for each element. That way, if we have multiple numbers with the same respective digit, we can store them. Let's show an example of radix sort. So let's say we have the following list: 64, 8, 216, 512, 27, 729, 0, 1, 343, and 125. For our purposes, we'll include leading zeros just to show the tens and hundreds digit. So with this algorithm, we're going to start by sorting the ones digit. That means we would get the following. We're going to get 0, 0, 0, 0, 0, 1, 512, 343, 64, 125, 216, 27, 008, and 729. So notice that all the numbers here are sorted by the ones digit. The next step is that we'll sort by the tens digit. Now here's the key observation as to why this works. The previous sort is preserved. Even though we're going to sort by the tens digit, the ones digit for the respective tens digits will be sorted. So what we would get is 0, 0, 0, 0, 0, 1, 0, 0, 8. So notice that for those three numbers, the tens digit was 0, but the ones digits are sorted in that group. We would then get 512 and 216. Once again, we have the tens digit here with this group, but the ones digits are still sorted. And then we'd have 125, 27, 729. Once again, we have a group where the tens digit is 2, but all the ones digits are sorted. We would then get 343 and 64. So then we'll sort by the hundreds digit. And once again, we're going to preserve the previous sort. So what that means is our final result is 0, 1, 8, 27, 64, 125, 216, 343, 512, and 729. This algorithm works because the only way that this could fail is if we get two numbers from the same bucket, but they come out in the wrong order. But as we saw in our example, the previous iterations ensure that whenever we have several numbers enter a bucket, they are going to be entered in sorted order. So this sorted portion will remain preserved. Therefore, the algorithm does work. Now, the running time of radix sort is O of P times N plus B. So what that means is P is going to be the number of passes, N is going to be the number of elements, and B is going to be the number of buckets. So we see here that if we're dealing with small numbers, then this is going to be a linear time algorithm.